Welcome back to the sixth and final section of Chapter 5. In this section, we will be looking at the law of cosines, in addition to a couple new area formulas for triangles. In the last section, we saw law of sines, which helped us solve some non-right triangles, but it was fairly limited because it didn't allow us to solve if we didn't know an angle and the side opposite. The law of cosines will allow us to solve those side angle side triangles as well as the side. When we only know all three sides, we can use it to find an angle and then solve the rest of the triangles. So we're going to look at that today. Our learning targets for the day: we're going to solve a triangle using the law of cosines, find the area of a triangle if possible, and that could also be find the area triangle using Herons Formula, use applications of the law of cosine, or solve applications using the law of cosines, and then use the law of cosines to determine if the statement is true or false. And that's basically the same as solving. They'd say that, oh, this side length is going to be 12, and you can use the law of cosines to find out that, wait, no, that side length would actually be 11, so that would be false. So that's just kind of a side piece. So, the law of cosines. First of all, remember we have our triangles, which are labeled with capital letters at the vertices, and then the lowercase letter opposite for that side length. So the law of cosines is actually very, very similar to the Pythagorean theorem, but the Pythagorean theorem only works for right triangles. The law of cosines expands it to work for any triangle. In fact, the Pythagorean theorem is really just a special case of law of cosines. So what is the law of cosines? Law of cosines looks like this. So triangle ABC is a triangle with sides and angles labeled the usual way. And we have three of them. That's just because it doesn't matter which side or angle we start with. Personally, I like the bottom one because that's the a squared plus b squared equals c squared. That's the Pythagorean theorem that we know. However, we have to subtract 2ab cosine c. So we have the 2ab cosine c. Now this is two sides and the angle in between them. This angle and this side are on opposite sides of the equation. Notice is actually the first thing and the last thing. So, and all three of these are the same. It's just what angle are we talking about? With the Pythagorean theorem, we were always talking about the 90-degree angle. Cosine of 90 equals 0. So that term goes away. But we were always talking about that because every triangle has a right angle, or every right triangle has a right angle. But now it doesn't matter. So let's look at a problem. We have triangle A, B, and C given that A equals 11, B equals 5, and C equals 20. So I would first draw and label a triangle. So we have A is 11, B is 5, C is 20 degrees. We're going to be finding A, little c, and angle B. So the very first thing that we're going to find here is that other side length. We have to find the other side length. So we have a side angle side triangle. So we have basically this entire side of the equation. So we just set it up to find the other side. So c squared will equal a squared plus b squared. So the other two sides squared, doesn't matter what order they're in, minus 2ab cosine 20 degrees. Now, just like with law of sines, these aren't going to be our special right triangles. You're just going to use a calculator for that. So we want to make sure that we're in degree mode. degree. Cosine of 20 is 0.939-ish. And then times 2 times 11 times 5 gives us about 103.36. Eleven squared is 121. 5 squared is 25. So we're going to go 121 plus 25 minus that number that we just found. And if we were looking at if C was an obtuse angle, that would be negative, and we'd end up adding this piece to it. Anyway, when we find all that, 121 plus 25 minus 103.36, etc., we get that C squared equals about 42.63381117. So we can square root. So C equals about 6.529. How many decimal places do you take it to? In this case, I would generally take it to 2 decimal places, like 6.53. But you take it to as many decimal places as the problem requests of you. Generally speaking, it'll say round to 3 decimal places, round to 2 decimal places, round to 1 decimal place. Follow the directions. So that's C. We have 6.529. Now we just need to find the other 2 angles. How do we do that? Well, we have all 3 sides now, so we could use the law of cosines to find another angle. But better than that, we have both angle C and side C. We have an angle on the side opposite it. We can use law of sines. You only need to use law of cosines one time in any problem. Just one time. Because then you have enough to use law of sines. Law of sines is decidedly easier to use than the law of cosines. So we could find either angle B or angle A first. Now, while you could choose either of them to find first, I would find not the biggest one first. Side A is the largest side of this triangle, which means angle A will be the largest angle of this triangle. It's possible it could be greater than 90. It could be obtuse. We'd end up with an ambiguous case that we would have to deal with and then cancel out one of the 2 possibilities. If you go for the smaller of the 2 angles, it will always be acute. So when you have a side angle side, you find the third side, then find the smaller of the 2 angles to avoid that whole ambiguous case issue. So we're going to find sine of B over 5 will equal sine of 20 over 6.529. So we can multiply by 5 to get sine B equals, let's go sine of 20 equals that, divide by 6.529. All the other decimals in that it's not going to make too much of a difference at this point in time. So we divide by 6.529, we get 0.0523 times 5 is 0.2619. Then we can go inverse sine to get B is 15.18 degrees. So we have everything except for angle A. To find angle A, that's the third angle, we don't need to use the law of sines or law of cosines. We can use subtraction. A will just be 180 minus angle C minus angle B. So 180 minus 20 minus 15.18 is about 144.82 degrees. Now, if you would have found angle A first, you would have gotten, instead of 144, you'd have gotten about 35.18 degrees. And then you would have subtracted to find B, which would have been a big angle. Then you would have had to realize that, oh, wait, the big angle should be opposite the largest side. And then have to go back and figure out what happened. That's why we found B. We found the smaller of the two remaining angles first. Now, if side C was the biggest side, like we found side C, let's say it came out to be 13, that's bigger than the other two. C is going to be the biggest angle. You can pick either angle to find first and not have to worry about it. But since it didn't, and just as a general rule, I always pick the smaller of the two angles to find first in this situation when we're dealing with that side angle side situation. But we're not always dealing with side angle side. Sometimes we have all three sides. So let's draw our triangle ABC. A, B, C. A is 9, B is 7, C is 5. So in this case, since we're using cosine, cosine will give us an angle between 0 and 180. Find the biggest one first, because it will give you that angle. You don't have to worry about that. So, being that 9 is the biggest side, let's find angle A first. What's important here is that they're opposite. 9 squared is going to have to equal something times cosine of A. So it'll equal B squared plus C squared, 7 squared plus 5 squared minus 2BC cosine A. So 2 times 7 times 5 times cosine of A. So in this case, we're going to have to solve for cosine A, then do the inverse cosine. First, let's just get our numbers. 9 squared is 81, equals 7 squared is 49, plus 25, minus 2 times 7 times 5 is 70, cosine A. 49 plus 25 is going to be 74, so we can subtract 74 from both sides to get 7 minus 70 cosine A, divide by negative 70. So we have negative 0.1 equals cosine A. Do the inverse cosine of negative 0.1 to get 95.74 degrees. So again, being that we chose the biggest one, it gave us the obtuse angle. We didn't have to worry about having to deal with that later on. So when you start out with three sides, find the biggest angle first. When it's angle side angle, you find the other side, then find the smaller of the two angles. Those are just pro tips. You could do it any way you want, but that does make it easier. So we found this angle was 95.74. Now we need to find another angle. For that, we can use law of sines. And now it doesn't matter which one we do. So let's see, we'll have sine of A, 95.74 over 9 equals, let's go sine of B, over 7. So we can do the sine of 95.74 divided by 9 times 7 to get it about 0.773877. I'm just going to write 0.77. I'll use the number in my calculator though. We're going to do the inverse sine of that to get 50.70 degrees. And now to find angle C, we can just go 180 minus those. 180 minus 95.74 minus 50.7 equals 33.56 degrees. And there we have the three angles to go with the three sides. This triangle is solved. So those are the two cases we can deal with law of cosines. With a side angle side, we have to find the side and then an angle using law of sines, or side side side, where you have to find an angle using law of cosines and then the second angle using law of sines, and then the third angle is subtraction. So how about the area of a triangle? Now we know the area is 1/2 base times height. Yes, that is true. That is not changing. However, we don't always know the height of the triangle because that's not a side length. So we have a different area formula that only involves some side lengths and an angle. 1/2 BC sine A, or 1/2 AC sine B, or 1/2 AB sine C. So when we have our triangle A, B, C, we know a side angle side. We know two sides and the angle in between them. We can find the area. We just go 1/2 side times the angle in between them. This is very similar to that last part of law of cosines, but that was minus AB cosine C. This is 1/2, no, it was minus 2AB cosine C. This is a 1/2 instead of a 2 and a sine instead of a cosine, and it finds the area. So let's look at one. Find the area of a rectangular octagon inscribed inside a circle of radius 9 inches. And you might be thinking like, wait a second, we're looking at triangles. True. Any regular polygon can be broken up into congruent triangles. So an octagon is going to be 8 congruent triangles. If we find one of them, then we can just multiply by 8. So we have one of them, so we're inscribed inside a circle, so we have side length 9 and 9. The angle here, we took the full circle and we split it into 8 different pieces. So our theta here is going to be 360 divided by 8. What's 360 divided by 8? 360 divided by 4 is 90, so divided by 8 is just 45 degrees. So let's find the area of one triangle. It's going to be 1/2 times B times C, those are both 9 in this case, times sine of 45 degrees. And we could multiply this all out and get a decimal, but this would be for the triangle. For the octagon, the area is just going to be 8 times this 1/2 times 9 times 9 times sine of 45 degrees. So 8 times 1/2 is just going to be 4. So we have 4 times 9 times 9 times sine of 45. In this case, it's 45 degrees. We know that's it's root 2 over 2. So we could get an exact answer here. But it's not always going to be 45 degrees. Usually you're going to end up using your calculator. So we can go 8 times 0.5 times 9 times 9, which is 81, times sine of 45, gives us an area of 229.1 1025. So we're going to go 229.1026 because it was 2597. So that I feel better about that. And let's see, it was inches. So this would be inches squared. So if we look at the picture, that should be just a little bit less than the area of a circle. Let's find the area of that circle. It's going to be pi r squared. So r squared, 91, or 9 squared is 81 times pi is 254.47469. So was that just a little bit smaller than that? Yeah. I mean, it was a little bit smaller than I thought it was going to be, but it is just a little bit smaller. This is just a check to make sure we didn't do something horrible and ended up way far off. So the area of our octagon is 229.1026 square inches. So there we can find the area of the triangle using two sides and the angle in between them. If we know those things, we can find that. In a right triangle, the angle in between the base and the height is 90 degrees. Sine of 90 is 1. It's a special case of this formula. Herons formula allows us to find the area of a triangle if all we know are the three sides. So if we only know the three sides, this will allow us to find it. And the equation looks kind of crazy, but it's actually not that hard to use. Because we have the three sides, then we have this word, the semi-perimeter. It's 1/2 of the perimeter. It's kind of like the average side, except instead of dividing by 3, we divide by 2. And then it's the square root of s times s minus a times s minus b times s minus c. What does that look like? We have triangle with sides 13, 15, and 18. So first we want to find s. 13 plus 15 plus 18, divide by 2. So that'll be 46 divided by 2, which is 23. So the area is going to be the square root. We're going to have 23 times, and then it's going to be 23 minus each of the sides. So 23 minus 13 is 10. 23 minus 15 is 8. 23 minus 18 is 5. We multiply these things together and we square root. So 23 times 10 times 8 times 5 is square root of 9,200. And so we square root that number to get that the area equals 95.9166 square units. Because we didn't actually get any units in this case. So, again, the equation looks kind of ugly because there's a lot of stuff going on there, but it actually isn't all that difficult to use. So let's look at a couple applications. First, let's take a baseball diamond. So we have a baseball diamond. It's a square, 90 feet on each side. The front edge of the pitching rubber is 60.5 feet from the back corner of home plate. So we have this, like something like this, it'll generally give you a little bit of a diagram to help with the explanation. It wants to find the distance from the center of the front edge of the pitching rubber to the far corner of first base. So it's looking for this distance right here. Now, the pitching mound is not, like, it is along that line from home base to second base, or home plate to second base, but it is not on the line from first base to third base. It's a little bit in front of that. So this isn't a right triangle here. Like angle B, there is not a right angle. So we have to use law of cosines. It's a side angle side question here. So we're going to have c squared is going to be a squared, 60.5 squared, plus b squared, 90 squared, minus 2ab, times cosine of c, which is 45 degrees. So in this case, we just need to do the calculations there, then we'll square root. So 60.5 squared is 3660.25 plus 90 squared is going to be 8100 minus 2 times 60.5 times 90 times cosine 45 is about 7700.39, etc. I'll just use that. So we'll have 3660.25 plus 8100 minus that 7700 gives us that c squared is 4059.857. Then we just need to square root that. So c is 63.717 feet. So it's 63.717 feet from the pitching mound to that back corner of first base. Like, they can't say to first base because first base is not a point. They had to pick a point, and that's where that measurement for 90 feet. It's not to the front of first base, it's actually to the back of first base. So that's why it's talking about the front edge and the back corner and stuff like that. But this is just an application of law of cosines. Another application, and this one's a fun one. A regular tetrahedron, it's a solid with 4 faces, each of which is an equilateral triangle. It's a triangular pyramid. Right, that's what a tetrahedron is. Find the measure of the dihedral angle formed along the common edge of 2 intersecting faces of a regular tetrahedron with edges of length 2. So the dihedral angle it's the angle of the faces. It's that angle, which is completely on the inside of the tetrahedron, because B is a midpoint on a side, so segment CB goes down the middle, it's the height of a side. Segment AB is the height of the side, and we're going to find this angle. We know those because if it's a midpoint, that cuts the side length into 1 and 1. The other side length is 2, so we have a 1, 2, root 3 triangle. This side length over here is 2, because that's the full side length. So, and that's the one opposite, so 2 squared will equal root 3 squared plus root 3 squared minus 2 times root 3 times root 3 cosine the angle. So 2 squared is 4, root 3 squared is 3, 3 minus root 3 times root 3 is 3 times 2 is 6 cosine B. We can subtract the 3 plus 3. So we get 4 minus 6 is negative 2 is negative cosine negative 6 cosine B. Divide by negative 6 to get 1/3 equals cosine B. And we can do the inverse cosine of 1/3 to get 70.5287. This goes 70.53 degrees. What's fun is that the side length being 2, that doesn't even have to happen. We can increase the size. It could be a side length of 10. It's going to be a similar figure, so the angle is going to be the same. You could factor 10 out of everything, and it cancels. So B is 70.53. So that angle, that dihedral angle, which is just kind of a fun word, is 70.53 degrees. So today we looked at law of cosines, the 2 different applications of it to find an angle if you have, or no, to find the third side if you have a side angle side, and to find the first angle if you have side side side. After that, we have law of sines to find the next angle, and then subtraction to find the third angle. We also have the 2 different area formulas depending on what information we have. So there's a bit going on. It's really just formula stuff though. So I will see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.